Hello, welcome back to trigonometry. Today we're going to look at a newer concept. Some of you may or may not have seen these before, but something called vectors. We're going to look at vectors and the operations that you can do on vectors. So that's going to be the focus of this one. Vectors are cool. You're going to find out, not as much in this lesson. This lesson you'll find out a lot about definitions and how to work with them, but you're going to find out that there's quite a bit of use of these in areas like physics, trying to look at physical problems. You end up using vectors to model situations. So those of you who are going to be going further in sciences, like into engineering or something, you really want to make sure you start learning everything you can about vectors. What are vectors? Well, first of all, a lot of the problems you've worked on so far just have things that are represented by real numbers. And we call those scalars. Scalars are quantities that involve magnitudes. So when I say that, they can be represented by real numbers. Okay. For example, a quantity like telling me, okay, the speed limit on I-4 is 70 miles per hour. When you told me 70 miles per hour, that's a real number. 70 is a real number. That's a scalar kind of quantity. Or if you tell me how much you weigh, tell me that you're 135 pounds, that's another scalar kind of quantity. Now, vector quantities will tell you magnitudes, but they also involve direction. So they involve magnitude and direction. Now you're going to look at what way they're pointing. So an example of that would be I was going 70 miles per hour east on I-4. So now I've given the magnitude, the 70 miles per hour, and I've given the direction I was traveling east. So we're going to look at all these different parts of vectors, definitions, and operations today. So we're going to be looking at these quantities that involve magnitude and direction. Okay, so how can we represent a vector? Often vectors will be drawn or sketched as these little arrows, and you'll have a starting point and an ending point. And they might label the vector with some kind of magnitude, and then you can tell direction often by angle. So like if you draw a horizontal here and you tell somebody that this is a 45-degree angle, then you can talk about this vector, about its magnitude and direction. Okay, so let's say we have this vector, the starting point might be labeled something like A, the ending point might be labeled something like B, and then the little arrow is showing you what direction you're going. It's telling you you're going from A to B, as opposed to like B to A. And in your book, you'll probably see the AB in bold. Like you'll see the vector name in bold like this. But when you're writing it, if you're just writing with your pencil or whatever, you don't need to try to do it in bold. You can write AB and put a little vector symbol over it. It looks like you're saying ray AB, but really in the context you're dealing with a vector. The point A is the initial point. That's the starting point. And the point B is the terminal point. That's the ending point. And your vectors don't have to be named with 2 letters. Oh, by the way, yeah, if your vector, if it was pointing the other direction with the arrow, by the way, this would be vector BA. You always start with the initial point and end with the terminal point. Now, if you want, you can also name vectors with just 1 letter. So like this might be vector U, and that's okay too. It's alright to name it just with one letter as well. Alright, and then if you want to talk about the magnitude, like vector AB and vector BA, they have the same magnitude, the length. But you're dealing with opposite directions there. Now how would you denote magnitude? Well, you can take the vector and write it between two bars. It looks like you're doing absolute value, but with vectors, and that denotes magnitude. So the magnitude of vector AB equals the magnitude of vector BA. You're saying basically here that they're the same length. Okay. Now if we want to talk about vectors being equal, equal vectors have the same direction and same magnitude. So you can always tell if a vector is equal by looking at the magnitudes and then looking at the directions. If vectors are equal. So like if you draw this as your vector A, and you draw that as your vector B, they have the same direction, same magnitude. So then you can go ahead and say that the two are equal. If they have same magnitude, different directions, they're not equal. Or if they have different magnitude, same direction, they're not equal. They have to have exactly the same direction and magnitude. So that's something about equal. And if they have the same direction, same magnitude, you can say they're equal. So it goes both ways, if and only if. Then sum of vectors. So I'm throwing a lot of definitions at you, but we're going to be using this stuff momentarily. Sum of vectors is also a vector. If you put like vector A like this, and then where A ends, see here's A's initial point, here's A's terminal point, where A ends, put B. As long as B has the correct angle, direction, angle, but in the correct length, you can put them together like this. The vector made from the initial point of A, let's do a different color. Vector made from the initial point of A to the terminal point of B, and I'm not doing it in bold, so I should do this, is the sum of A and B. Or another way to look at it, if they both have the same initial point, and let's say we have it situated like this. Notice B is still at the same angle, it's just situated at the same initial point as A. Then the sum can be found here. And it turns out that you can make a parallelogram. If you put another B here, if you put another A here, you can make this little parallelogram. And the diagonal, whoops, I switched colors. The diagonal of the parallelogram is A plus B. So that's handy to remember if you're trying to deal with sums. You can geometrically talk about the sum either by taking the initial point of A to the terminal point and then taking the initial point of B at A's terminal point and going, and then going from initial to A to terminal of B. That resultant vector there is the sum of these two. Or if they both, A and B, have the same initial point, the resultant vector is going to be the diagonal of a parallelogram that you could make by repeating A and B over here. So that's something to think about, to keep in mind when you're working with these. Vector addition is commutative. If you take A plus B, it's the same thing as B plus A. And remember, the A plus B, that's the resultant vector. Okay. Now where there's a plus, there can also be a minus. If you have vector B like this, minus B is the same length in the opposite direction. Okay, so the minus B is the opposite of B. And the sum of those two, B plus minus B, is going to give you the zero vector. Has magnitude of 0. There's no direction to it. Now if you wanted to do the sum of like A and minus B, you have to think about what's happening with A and B to begin with. If you had A here and B here, keep in mind that minus B would be going in this direction. So when you go to do the resultant vector with A minus B, you would have it right here. You got A and minus B. Resultant vector would be in there, because you could still make one of those parallelograms just with A and the minus B instead. So that's something else to think about. All right, so that's giving you some geometric ideas about vectors. Let's look at these algebraically as well. The addition, the subtraction, and all that stuff. Let's look at them algebraically. Well, let's draw coordinate axes real quickly here. Oh, I don't like that. Let's just do segments. Okay. Let's draw coordinate axes. X, Y axes. And let's put a vector situated like this, so that its initial point here is at the origin, and then its terminal point out here is some ordered pair AB. Okay. Now the angle that the vector makes with the positive x-axis is theta. And we call this vector a position vector. So let's go ahead and let's call this vector u. Vector u is a position vector. You can take any vector you're working with, you can situate it on the xy axis system. with vectors, they have to maintain the same length and same direction, but you can move them around on your paper to for convenience sake. You know, if you want to like situate it so B starts where A ends, and B wasn't on your paper there in the first place, you can still move it as long as B has the same direction and same magnitude. So you can situate any vector you want really on the coordinate grid here and start looking at things in terms of position vectors. If the initial point is at the origin and terminal point's out here, the position vector u, you don't have to call it u, but you know, it's a common thing to call it that. The position vector u, you can say equals a comma b. With this notation, it looks kind of like an ordered pair, but it's like little pointy parentheses. That lets us know we're talking about a vector, and the values in here tell us the coordinates of the endpoint of that vector. We know the initial point's at the origin, the endpoint's at these coordinates. So that tells us quite a bit about that vector. And knowing where the endpoints are, we can also figure out information about theta, which is the direction angle. Knowing that, because the vector does have direction, not only magnitude but direction. So theta is the direction angle. Alright, so that A is considered to be the horizontal component, and that B is considered to be the vertical component. So you've got position with the AB, you've got direction with the theta. And then you're able to work from there. The magnitude and direction are related to these components. What you've really got yourself here is it's like you're back at the unit circle or back at, you know, right triangle trigonometry. You've got a right triangle here. The magnitude of the vector u, the position vector, the magnitude of that, the length of that, can be found basically using the Pythagorean theorem. The length of that's going to be the square root of a squared plus b squared. Because Pythagorean theorem, a squared plus b squared will equal c squared. Well, the square roots, to get c, you get square root of a squared plus b squared. C is really the length or magnitude of vector u. Then theta, if you look at theta, the tangent of theta is going to equal b over a. And of course a is not zero, a can't be zero in that case. And that direction angle is always going to be a positive angle. So we're looking at, you know, what's the angle coming off of the x-axis, positive x-axis, in that counterclockwise direction. And that's going to be our direction angle. So we got to look closely at that. Okay. So let's do a problem or two where we're, you know, working with these formulas basically. All right, let's say we have a vector u, position vector u, and we are given -5, 4, and we want to find the magnitude and direction. Well, for the magnitude, just do the square root of the -5 squared plus the 4 squared. So we got square root of 25 plus 16, which is the square root of 41. And there's our magnitude. Now for the position angle, let's think for a minute what -5, 4 means. It means our vector is here in quadrant 2 if we draw on the y axis system. Because the -5, 4 is basically like the coordinates of the endpoint for the vector. And when we're trying to find theta, we're looking for this angle here. So the magnitude square root of 41, that's the length of the vector. Theta is that position angle. So tangent of theta would equal opposite over adjacent. So it's going to be 4 over negative 5. So to get theta, we'll do the inverse tangent of negative 4/5. Let's go ahead and find this in degrees. Let me pull up my calculator. What mode am I in? I'm in radian. I want to do this in degrees, just because that's what the example problem's doing it in. So that's what I want to do it in too. So we're doing the inverse tangent of negative 4/5, and we get this. Now the position angle though has to be positive angle. They're giving us negative 38.6598. They're giving us the inverse negative, but remember, when you're doing inverse tangent like that, it has to be doing inverse tangent from previous lectures. The angle has to fall somewhere from negative pi over 2 to pi over 2, or negative 90 to 90. But we're actually looking at this angle here in quadrant 2. So rather than looking at negative 38 here, we're going to need to add 180 to see what our angle is. So let's take the calculator and add 180 to get the correct result, to get the correct quadrant here. And we get this. So we get around 141.3 degrees. So we have to be careful and watch for our quadrants and make sure it's a positive theta. But there you go. That's the magnitude and direction angle there for that position vector. Okay. Now we can take this and go even further, and we can say we can find those horizontal and vertical components. Let's say we know the magnitude and direction angle. We can kind of work backwards and find our components too. Think about what's happening here. Let's go back up to what I had at the top, that drawing, or not the top, but up to here. If you look at that drawing carefully, you'll realize that the cosine of theta is going to be adjacent over hypotenuse, so it's going to be that length A over the length of that position vector. Or you could say that A is the length of that position vector, the magnitude of that position vector times cosine theta. If you know the magnitude and direction angle of the vector, you can work backwards and find its components. Because also sine theta equals opposite over hypotenuse. So B, that vertical component, is magnitude of the vector times sine of the angle. And that comes from basically the right triangle trig right here. So let us go down and let's take an example where vector V, we're told, has a magnitude of 14.5, and we're told that it has a direction angle of 220 degrees. And we want to know the components, horizontal and vertical components. Okay, so this vector, looking at it being over here, has a length of 14.5, and then this angle is 220 degrees. And we want to see what A and B are. Okay. Well, now we know that A is going to equal the 14.5 times the cosine of 220. So we find that, we'll be able to find A. We also know that B is going to be the 14.5 times the sine of 220. So when we find that, we'll know b and be able to use those components. So 14.5 times cosine 220, and we get around negative 11.1. And then 14.5 times sine of 220, and we get around negative 9.3. So then we can express that vector with its components. Do the little pointy parenthesis kind of thing. Negative 11.1 comma negative 9.3. Close the pointy parentheses. And now you've talked about that vector with its components. So you know that you have a negative 11.1 on the x-axis, negative 9.3 on the y-axis, and that tells you where you're located with your terminal point. Because the initial point you know is situated on the origin. Alright, a little slight continuation of that. If they give you, let's say they give you the magnitude and direction angle and it's something you can work with on the unit circle. Let's say they tell you that you have vector u that has magnitude 8 and theta of 135 degrees. But when you go to do your vector, you can do magnitude times cosine of 135 for the horizontal component, and you do magnitude of 8 times the sine of 135 for the vertical component. On your unit circle, you can get cosine and sine of those. Cosine of 135 is negative square root of 2 over 2. Sine of 135 is positive square root of 2 over 2. So you get negative 4 square roots of 2, comma 4 square roots of 2. That's for the vector u. If it's not on the, if you don't have the angles on your unit circle, then put them in your calculator and see what that comes out to. But you can continue working with those same formulas to find, using magnitude and direction angle, you can find your components of your vector. Okay, finding magnitude of a resultant vector. Let's say you have a question that says two forces of 32 and 48 newtons act on a point in the plane. We're going to act on the same point. So you might, let's say you have some kind of load, and they tell us that, and they're telling us that, let's say you have a load, you're trying to pull 2 ropes or something, or 2 chains. One of the ropes or chains is being pulled, applying a force of 32 newtons. The other is applying a force of 48 newtons, and the point in the plane might be your load. And they tell us that the angle between the forces is 76 degrees. So maybe your ropes are at a 76-degree angle. R, what am I thinking? Erase that. Angle between forces is, 76 degrees. Dang, it won't do what I want it to do there. Okay, 76, draw the 6, thank you. Alright, angle between forces 76 degrees. So you might, your one vector, like you have this point, this load or whatever, you got the 32 newtons. The other vector, you've got the 48 newtons. And you know the angle between is 76 degrees. And you're asked to find the magnitude of the resultant vector. Okay, so you've got your, let's say you have your load sitting here. You've got one rope pulling this direction with a force of 32 newtons, another rope pulling that direction, force of 48 newtons, angle between 76 degrees. Your load is going to move along the resultant vector line. And the magnitude is going to tell you how much force is truly being applied to that load when you have two different ropes. So how much force will the sum total be? And they want us to find the magnitude of that force vector. Because force, you've got magnitude and direction. Because apply a force in a certain direction, and things are going to move in certain directions, and so forth. So we're going to let's resketch this for a second. We've got one that's 32 newtons. If we've got one that's 32 newtons here, and we've got another that's 48 newtons here, the resultant vector is going to be going down the center here. But let me kind of sketch the parallelogram out. I like to have dotted here to complete the parallelogram. Because when you're adding vectors, or looking at resulting vectors, the resultant vector, I don't like the way that's going, the resultant vector is the diagonal of this parallelogram that you can do. Okay, so 32, 48. So the resultant vector would start here and go to here. Okay. So we'll just call it V for now. Resultant vector V. And we're interested in finding the magnitude of V. Well, if we look at this a little more closely, we know that this angle here is 76 degrees. Well, with this being a parallelogram, these two angles have to be supplementary. All four angles together add up to 360. Opposite angles are congruent. And in order to add up to 360, these two have to add up to 180, these two have to add up to 180. So that means this angle here must be 104. And so must this angle. Well, we don't have a right triangle, but we do have side angle side of an oblique triangle, and we learned about the triangles with the law of sines and law of cosines a while back. We can apply law of cosines here. We've got this 32, we've got that 48, we've got this angle here. We can apply the law of cosines. The length of that vector here, that magnitude, that length of that side of that triangle squared equals the lengths of the other two sides, each squared, 32 squared plus 48 squared, minus 2 times the 32 times the 48 times cosine of the 104 degrees, the angle in between them. If you put that in your calculator, the magnitude of V squared equals around 4,071.184063. And then if you do the square root, the magnitude is you're going to get 63.80. And it's a positive square root because we're dealing with length here. 80583095. So we round it. You can say the resultant vector, the magnitude is roughly 64 newtons. And there you have it. Okay, one more thing. We're going to talk about vector operations, and then that will wrap up this introduction to vectors, but you want to stay tuned, come back, tune in again, because we're going to be continuing with vectors. We're going to end up talking about the dot product and properties of the dot product and geometric interpretation of the dot product, and then we're going to get into more application kind of problems. So you don't want to give up here. You want to come back, tune in again on the next podcast. But for now, let's just look at one more thing. Let's look at vector operations. Okay, if you have vector AB plus vector CD, that equals vector A plus C, comma B plus D. Okay, so let's say you have vector U is 6, negative 3. Let's say vector V, you've got negative 14, comma 8. So U plus V, you're going to take the 6 plus the negative 14, comma the negative 3 plus the 8. So you're going to get negative 12, or I'm sorry, not negative 12. Oh my gosh. 6 and negative 14 is not negative 12. Just making sure you pay attention. Haha. You get negative 8, comma 5. And that's the resultant vector. If you have some constant k times the vector AB, then you're going to have vector with Ka, comma Kb. Alright, so for example, using same vectors u and v, let's say you have negative 1/2 times v. Well, you take vector v, take negative 1/2 times the negative 14, comma negative 1/2 times the 8, and you will get 7, comma negative 4. But still, it's a vector result. And notice too that your vector v was negative 14, comma 8, and as soon as you multiply by a negative, the signs inside changed. Went from negative to positive and positive to negative. So then if you put it together, let's say you had something like 5u plus 2v. Well, the 5u, you would do 5 times 6 and 5 times negative 3, which would give you 30 and negative 15. Then the 2v, you would have 2 times negative 14 and 2 times 8, so you'd have negative 28 and 16. And then to add those together, you'd be adding the 30 and the negative 28, and you'd be adding the negative 15 and the 16 together, and you would get 2, comma 1. So that's when you throw them all together. So there's a little bit about vector operations. So again, tune in again. We still have to talk about unit vectors and go on into dot products, which are very important for our vector application problems. But in the meantime, thank you for joining us. Look forward to seeing you again.